Okay, so here we have a projectile motion example where something is being launched from ground level with an initial velocity of 15 meters per second at an angle. I'm going to be careful here that I don't. There we go. So that's a 70-degree angle. And here's the trajectory. You're going to see. Like so. Now, I'm going to replay that and then stop. And you'll notice here that there's a green arrow and a yellow arrow. The green arrow represents the velocity, the current velocity, the instantaneous velocity of that cannonball, and it's in a continual state of change. As it's rising, it's changing direction and it's also shortening. And then as it falls, it's going to change direction and also lengthen. So here we have, so you see that? I mean, it took place pretty quickly, but I mean, this is obvious, right? As it goes up, it's going to slow down. But at the top here, it did not come to a dead stop. Let's watch that again. I'll slow that down this time so we can kind of watch it. And you'll see that green arrow. It will not shrink. I mean, because there's always some velocity there sideways. And the yellow arrow, let's try that again. The yellow arrow is the acceleration due to gravity. It is always pointing straight down and it never changes. So once an object is in free fall, it's been released, the acceleration is always straight down, it's always 9.81 meters per second squared, and it doesn't change, even though the velocity is changing throughout the flight. Now I can switch this, and instead of looking at the overall velocity, I can look at the components of the velocity, and this will be interesting. So now and I'm going to keep it on slow. So here you can see that there is let's freeze that. And there is a horizontal component to the velocity, and there's a vertical component to the velocity. And then the yellow arrow here is the acceleration due to gravity, excuse me, which is not changing at all. And let's let that continue. Okay. If you focus your attention on the horizontal one, you will notice that it never changes. Just watch. The horizontal component of the velocity does not change, but the vertical component of the velocity is in a continual state of change as we go through this motion. Let's watch that one more time. So horizontal never changes. The vertical is shrinking to zero when you come to the highest point, and then it lengthens in the downward direction, like so. So we can break down the velocity into horizontal and vertical components. So this is what I showed you how to do yesterday. We have a vertical component to the velocity right here, and this is the Vy is going to be 15 sine 70 degrees. That's the initial Vy, and that's going to be, in this case, 15 sine 70, which is 14.1. So I might as well put in the 3 digits here because it'll make my numbers work right. So 14.1 meters per second. And the x-coordinate of the velocity, the Vx, is going to be 15 cosine 70 degrees. And when we do that calculation, we get 15 cosine 70. It's going to be a lot less. 5.1. 5.1 meters per second, like that. So when it initially starts to rise, this is the V velocity. It's going to be 14.1. When it reaches the top right here, the Vy is going to be 0. But the Vx is not going to change. The Vx is going to be 5.1. So that's why we have that green arrow here, and it only has a length of 5.1 this way. And there is no Vy velocity. But then as it starts to fall, the Vy is going to start to pick up. And when it eventually reaches the ground right here, and when it's smashed, I'm going to try and draw this arrow. the same way that it's drawn at the beginning. At this point, now we have a Vy is going to be minus 14.1 meters per second because it's going to gain back all of that vertical speed because it's back to the same level that it was launched at. And the Vx never changes. That green arrow you saw is the horizontal velocity that never changes. So let's have a look at that again. It's in slow motion, so let's see. For some reason I have to hit this multiple times. So you can see here now, there's the 5.1 meters per second sideways, and this is the vertical component of the velocity, which is shrinking as it rises. And then when we get to the top here, you see that? It completely disappeared, the Vy. And as it comes down, now we have a Vx component, which is 5.1, is never going to change. And the Vy is going to increase in the downward direction. And the overall, so this would be your, if you drew this line straight out here, that would be the overall. I don't know if this will work midstream. Oh, yes, it does. See, I can switch back and forth. There's the total velocity, and here it is broken down into components, into the Vx and the Vy. And down we come like this. So the moral of the story is the Vx never changes. Turn that back here. So the Vx is a constant. And it is, well, in this case, it's 15 times the cosine of the angle. I don't want to write that down because if I use this angle here, it would turn into a sine situation. It's constant, and this determines your horizontal displacement. What I mean is this. Your x is going to equal Vx times t, where the t is how many seconds it's airborne. How long is it in the air? And if you want to find out how many seconds it's in the air, what we do now is, and so I'll just call this, call that 1. The number of seconds in the air, the time in the air is only determined by the initial velocity. So here, our V0, our initial one, is 14.1 meters per second. When it lands, so this only depends on, it's only the Vy that matters. The Vx doesn't do anything to the time of the air. And so here we have our final V is going to be minus 14.1 meters per second. Our acceleration is going to be minus 9.81 meters per second squared. And our time in the air is going to be V minus V0 all over A, which is minus 28.2 over negative 9.81. And that's going to give us 28.2 divided by 9.81. And that's going to give us 2.87 seconds. So that's the total time that it's in the air. The time to go to the maximum height will be half of this. But we can use our tool here now, which I've brought down, and place that over here, 2.87 seconds, 2.87 seconds. And right at the top, it's 1.44, which is half of that. So now we can continue number 1, and we can get the x is going to be the Vx, which is 5.1, multiplied by 2.87, and this will tell me how far sideways the projectile has gone. 5.1 times 2.87 equals 14.6. Now, I don't know if that's going to work perfectly because this 5.1 is rounded. So here is, again, I can take this, and this will give me the range. Oh, look, 14.7. 14.6. So it's very, very close. Almost perfect. So just to recap, if you want to find out how long or how many seconds a projectile is in the air, if it's going up and returning to the same level, okay, that's key. we can make some assumptions here. The only thing that determines the time in the air is the vertical component of the velocity. The horizontal component does nothing. The initial velocity is going to be the vertical component. The final velocity will just be the negative of that because all of that vertical speed will return by the time it hits the ground. The acceleration due to gravity will be minus 9.81. It never ever changes. And the time in the air is, you just use your kinematics equation. Once you know the time in the air, now you can figure out how far sideways you've gone, because the sideways velocity is constant. It never changes. So we don't need to use the kinematics equations on the sideways motion. We can just use this. The displacement is velocity times time. We figured out the time. We know the horizontal velocity, which is never changing. Multiply that together, and we get the range. So that's how you get the time in the air and then the range.